The New South Wales Automotive facility is a project involving a factory, residential area and port. These facilities are to have the capability of constructing 500,000 electrical vehicles per year. This is in order to help reach the government's Road to Zero strategy. The facility itself is to be constructed near to the small town of Undy. This location was chosen due to the ample open space as well as the proximity to existing port facilities. The project itself was undertaken by Fortis Engineering Solutions. Fortis is a multidisciplinary engineering consultancy containing engineers from civil, coastal and mechanical engineering disciplines.
The purpose of this project was to provide the UK with an incredible manufacturing opportunity to make the country a world leader in electric vehicle production, providing 500,000 vehicles a year, equating to one per second. The project also wanted to pave the way for a more philanthropic business model for modern companies. The inclusion of low-rent houses for workers, based on Bourneville and Birmingham, was an important feature for Fortis. The project also involves a port facility that ensures the complex has import-export capability and an entire infrastructure system due to being built on a greenfield site.
The core values of Fortis are as follows. Safety, to ensure the safety and well-being of staff and clients above all. Integrity, to ensure morals and ethics take precedence in all company decisions. Continued development, to ensure the constant development and evolution of Fortis. Sustainability, to ensure sustainability is at the core of all work undertaken.
As well as being invested in advancing the adoption of electric vehicles in the UK, Fortis is an organisation that is passionate about providing engineering solutions. The company consists of a diverse engineering skill set, has strong values integrated into its code of conduct, champions collaboration at all levels, adapts to market requirements, and cares about the wider impact on the environment.
The project team involves 10 engineers from various engineering disciplines. Carl Smith is the project manager for the Fortis team. He is responsible for team leadership and making sure that the project runs smoothly. Lauren Wade is the lead civil and coastal engineer for the team. She oversees all of the civil and coastal aspects of design. Lauren was responsible for undertaking the design of the factory and warehouse. Oliver Hill is the lead mechanical engineer on the team. He oversees all of the mechanical aspects of the project and was the main mechanical input for the factory interior. Oliver is also responsible for the project finances. Jake Barham is one of the 2 coastal engineers on the team. He was the health and safety officer for the project as well as one of the primary sources of input for Zone 3. Nathan Thompson was the 2nd coastal engineer for the team. He was also the risk officer for the project. Nathan worked primarily on Zone 3. Tim Jansen is one of the civil engineers working on the project. He was responsible for undertaking the outline design for Zone 2. Cheyenne Mary Daly Shomney is another civil engineer. She worked on the utilities within Zone 4. Edward Hunt is a mechanical engineer who is primarily responsible for power generation design within Zone 4. Robert Humphreys is another mechanical engineer. He was responsible for designing the mechanical systems within the warehouse as well as managing quality on the project. Kyril Norman is a mechanical engineer specialising in marine technology. He was responsible for designing the mechanical systems for Zone 3.
Regulation compliance within the designs was key in the development of the project, with Fortis currently undergoing assessment for ISO 9001 and ISO 14001 certification. Alongside the integrated use of BREEAM standards in the detailed design process, the development of the facility has been ensured to meet general guidelines for development, with relevant specific standards used for all aspects of the design. In order to reach the government's Road to Zero strategy, a factory has been designed with a capacity to manufacture 500,000 electric vehicles per year.
The sheer size of the building required meant that structural design would be extremely difficult. This was combated by designing a 100 metre by 100 metre symmetrical block that both the warehouse and factory could be based on. Clear spans of 50 metres were achieved through the Virendale trusses. Further to this, several brace bays were required to provide lateral stability against wind loads. These also provided the cores for the lifts needed for the mechanical logistics system. This solution provided the most freedom to the mechanical engineers so that their layouts were not constrained by structural elements, which was deemed one of the most important parts of the design.
A high degree of automation has been implemented, with 540 employees every shift working alongside over 2,000 different pieces of machinery. The factory has been divided into 3 main areas: manufacturing, assembly and logistics, each utilising Industry 4.0 technology to provide an integrated system of systems that will streamline the production of vehicles to customers using the very latest technologies. A large proportion of the components within vehicles will be manufactured on site from raw materials, with over 1,000 tonnes of steel arriving every day from the steelworks located within 10 miles of the site. All materials used by the factory will enter via the warehouse. Due to the lack of manufacturers within the UK capable of supplying the batteries for electric vehicles in the amounts required, on-site production has been designed with an estimated production rate of 7.6 million cells per day, roughly equivalent to 50 gigawatts of energy storage produced per year. To facilitate production, a fleet of over 1,000 autonomous vehicles will ferry materials and components between manufacturing and assembly areas via the upper factory floor using lifts. The use of this floor enables logistics to be handled separately from the production processes, allowing the components to be protected from debris. The use of Industry 4.0 technology is of high use in the operation of these vehicles, with wireless networks enabling a flexible system to be used that is able to reroute and reassign materials instantly if a fault is detected, minimizing the effect on production. Components will then be loaded onto automated vehicles for assembly, reducing human interaction with hazardous manufacturing processes such as welding and painting. The matrix production system used by this factory utilizes a system of interchangeable assembly cells, each capable of performing the actions of the others, allowing for complete flexibility in the case of system faults or complex tasks that require additional time for assembly that would hold up the production of other units in a conventional production line layout. The Industry 4.0 system will be capable of identifying these hold-ups and rerouting awaiting units to other free cells for assembly. Once the automated assembly processes have been completed, high dexterity components are to be installed by teams of workers in the finishing areas. From here, each vehicle will undergo a half-an-hour quality check to test all functionalities of the finished product for the highest customer satisfaction. From here, the finished vehicles will be transported by automated vehicles to the vertical car storage towers to await transport or collection by the customer.
Zone 2 provides living space for 3,000 workers and their families. The accommodation area is to be positioned within walking distance of the factory and far enough away from the M4 motorway to create a quiet living space for occupants. General facilities will be provided for a good quality of life. Examples of facilities implemented are educational facilities, leisure centres, commercial spaces, supermarkets, and vast amounts of parks and green spaces. Two types of main accommodation are planned. The first will be a family house, of which 2,000 will be built, providing housing for 8,000 residents. The second type of accommodation is a flat, aimed at younger residents and couples without children. 42 flats are planned to be constructed and would provide housing for 4,000 residents. Flats will also save on space for the project, which will help with cost and flooding caused by urban expansion. Due to the vast urbanization of the project, the residential area will also have to be protected against flooding. This was done by utilising the most relevant and modern SUD schemes. The main SUD scheme is 2 retention ponds. For these ponds to be effective, a surface water drainage network was designed and implemented. Along all roads will be a beanie block combined curb and drainage, which combines a standard curb and drainage for surface water runoff. Green space was also added, using roughly 20% of the total residential area for flood mitigation, as it reduces the impervious area and therefore reduces the peak runoff coefficient, relieving the stress on the neighbouring retention ponds. The final SUD scheme implemented will be the use of permeable paving, provided in all major car parks and designed to Marshall's design guide, further reducing the capacity required for the retention ponds. Creating a residential area which considers all types of residents and facilities and then combines these throughout the area will create economic and social diversity, which is key to the success of a residential community.
The port is a vital part of the Automotive compound project and has been designed to handle a proportion of the factory's imports and exports. The design was put together with 3 key factors in mind: the economy of the project, the efficiency and safety of transporting goods, and the environmental impact of the project. The port has been designed to be a fully excavated site with no reclamation of land within the estuary, to ensure minimal negative impacts on local wildlife and habitats, whilst also increasing the ease and decreasing the cost of construction. The 7-kilometre long access channel will connect with the existing Bristol Channel. The high tidal range in the area generates difficult water depth and current conditions to work with, but the channel has been designed to allow access into and out of the port for at least 50% of the day. A higher time window than required, this minimises the amount of dredging required and puts the safety of the vessel movements first. Circular caisson walls have been identified as the most cost-effective and structurally sound option for this port. This is because they allow for a simple construction method in which the wall can be cast in place. Once completed, they will be able to withstand large forces, allowing for the use of large cranes and a storage yard relatively close to the wall. A key design consideration for any port is seiche, the development of standing waves within a port basin due to variations in air pressure. The circular outer face of this wall dissipates the energy of any developing wave, nullifying the likelihood of excessive ship movement and structural failure. The port will follow the operational procedures of UK Port Maritime Operations, complying with the UK Marine Safety Code. 4 container cranes are used for better control of loading and unloading processes.
The infrastructure has been designed to provide the New South Wales Automotive facility with all the physical systems of society that are necessary for the project to thrive. Clean water on demand, safe and simple transport, and superfast broadband are ensured through connections to local services. Comfort and well-being for the community comes in the form of open green space and physical security measures in the home and the workplace.
To provide reliable power to the complex, the power generation design consists of 6 gas turbines and 3 steam turbines arranged in a combined heat and power configuration, which is designed to maintain an output of 143 megawatts of power and 292 megajoules of heat. This has been calculated to be capable of powering and heating the entire complex in the most efficient manner, with redundancies to ensure continual operation, at a cost lower than that offered by the national grid.
Before construction begins, all necessary site investigations will take place, such as ground investigations to assess the suitability of the foundation design, as well as detailed topography reports of the estuary to aid the design of the access channel. Construction of the project will take place over a period of 3 years, with the construction of each zone being staggered over that period. The first zone to be constructed is Zone 4 to establish infrastructure for the site and allow for better access site-wide.
Throughout the project, risks were recorded in a live log in accordance with the risk matrix based on the British Standard ISO 31000:2018. Ratings of likelihood and severity were multiplied to create the overall risk rating. Moderate risks were reviewed in weekly meetings to assess any changes which could affect the project. A total of 64 risks were recorded. The increasing political and commercial demand for electric vehicles, as well as the versatility and market dominance this factory can ensure, are the chief factors in the reduction of risk for this project. Risks are reduced both by the size of the factory, making it an essential asset for the UK economy to remain competitive following Brexit, as well as the on-site port, allowing fast access for imports of raw materials and exports of our finished product. The total procurement costs for this project have been estimated to be for £7.743 billion, with recurring costs expected to be in the region of £494 million each year. Zone 1, the manufacturing complex, accounts for 74% of the construction costs of this project, equating to £5.426 billion for the construction of the building and the procurement of the equipment needed for production. The recurring costs have been estimated to total £494 million per year, with £397 million of this being from the supply of gas to the heat power generation facility. From the construction timeline created, a profit and loss forecast was generated, where it's determined that the break-even point of this project would be in the 5th year after the start of construction, around 2.5 years after electric vehicle production commences. The New South Wales Automotive facility boasts careful repurposing of a floodplain, intuitive use of space that allows workers to live close by in areas that promote community, and most excitingly for the future of the UK automotive industry, a smooth automated electric vehicle production line with the ability to accelerate the UK towards its 2050 objective of full electric vehicle adoption. The production line will produce 500,000 state-of-the-art cars per year, with a prospective return on investment after only 2.5 years of production.
Fortis Engineering Solutions, working for you.